So for this problem, given that a resistor consumes 20 watts before being turned on at t equals 0, after t equals 0 we have this voltage. Voltage with respect to time equals 100 e minus 2t, and the unit is volts for that. And that's for any t is greater than or equal to 0. The question that we're being asked is find the total energy consumed by the resistor at time is greater than or equal to 0. So with this, the first thing that we're going to do is we're going to see what equations we have that are useful. So the first equation that is useful to us is power equals current times voltage. Power equals current times voltage. So we're going to be able to manipulate this a little bit because right now we're looking for total energy consumed by the resistor. We're going to change this into the amount of current before or at t equals 0 to find that. So what we're going to do is we're going to go to rearrange. So current equals power over voltage. So all I did was I pulled this one, so the P comes down underneath, and that equals I. So I equals P over V. So what do we got for this one? At t equals 0, remember, we go back up here, we've got 20 watts as our power. So we're going to go back down here and do 20. And then for our voltage, we've got this interesting function. So we're going to plug this interesting function in here, 100 e up minus 2t. And remember, this one is in watts, and then this one is in voltage. Just keep it on the side just so you don't remember. So this is the general. So if we're looking at t equals 0, we can plug t equals 0 into this, and that's e up negative 2 times 0, so e up 0, which is 1. So at t equals 0, we're going to get the nice thing of I equals 20 over 100 times 1. Remember, the unit for I is amps, so that's going to equal 0.2 amps at t equals 0. Cool, so that's the first starting point. But now the question is asking us for the total energy consumed at any time greater than t. So what we have to do now is take this equation that we just found, and we're going to have to use another equation to solve that. So we've got P of t, so power with respect to time equals the voltage with respect to time times the current with respect to time. So now we're all in the time domain here. So we're going to be able to plug that in. Power with respect to time to find the instantaneous power of this is going to equal P of t equals the voltage with respect to time is that same equation that we had over here. So with that, we're going to pull this in, and that's going to be 100 e to the minus 2t. And then we're also going to have the current with respect to time as well. So current with respect to time, we're going to use our 0.2 e up minus 2t. And remember, that comes from this, because we have current, oops, let me move that over. Current is this equal to this equation. So current with respect to time is going to be that 0.2 to the negative 2t, and that's going to be current. So we're going to pull that piece out too. So we see two different pieces here, both with negative 2 and negative 2. We know some very simple math that we can use to be able to simple this out a little more. So that's going to be P of t equals 0.2 times 100 equals 20. And then we're going to go E, and then we're going to collect terms up here to the minus 4t. And that's going to be our instantaneous power, and that's going to be in the units of watts, of course. So this is saying at any instant in time, specifically one instant, what is our power in that circuit. Now, we don't want any instant. We want the total energy consumed. So that's going to be every single instance that exists. So how do we find that? if we have a whole bunch of individual points and we're trying to get something with all of the area under that curve, that naturally says that we're going to have to integrate. Also, this p of t with units of t is generally a good sign that integration is coming as well. So what we're going to do is we're going to do our w equals the integral from 0 to infinity of p of t dt. So this is saying the total energy is the integral or the sum of all of these little points of instantaneous power, all these little points of instantaneous energy with respect to time. So with that, we're going to be able to add a little bit more in there. We're going to do the same integral, 0 to infinity of 20 e to the minus 4t. And we got that from this equation that we just solved for before. 20 e to the minus t, and I should do dt because we're integrating with respect to t. So if we integrate this, we're going to come out with w equals the integral from 0 to infinity of minus 20, and we're going to pull that 4 down. The 4 actually, the minus goes with actually the 4, but you can get minus 20 over 4 e to the minus 4t. And then to solve that, we're going to do w equals minus 20 over 4 e to the minus 4t from 0 to infinity. And if we plug infinity into minus 4t, e minus infinity is going to go to what? It's going to go to nothing. And then if we plug 0 into the minus 4t, e up minus 4 times 0, so e up 0 is going to be 1, so that's going to cancel out too. So for one of them, we cancel the entire thing out, and the other we cancel 1 out, so that's going to be w equals 5 joules. Cool? And so what's that saying is the total energy from t is greater than equal to 0 is going to be 5 joules of energy.